I'm going to talk about some joint work with my colleague Aaron Sidford and Kiran Charikar, who's jointly advised by Aaron and me. I'll show you a little bit of our journey in thinking about this problem. I should say that Kiran is really responsible for getting us both started thinking about this question, which is a little bit outside the immediate interests of both Aaron and me. And this is something that Kiran picked up at a Fox workshop, was all excited about the problem, and then he recruited the two of us to work on it. And it's been a fun journey, and I'll tell you some of the things that we found out along the way. So let me start with the central notion that we're going to talk about in this talk, which is profile maximum likelihood. There's a bunch of jargon in that title, so I want to try to unpack that for you first. Let's consider the following setting. Okay, so you have some unknown distribution P over a domain of size n, and we'd like to estimate some property of this distribution. Okay, so what is this property? Let's just say, we'll say that in a second, but what access do we have to this distribution? Let's say the access that we have to this distribution is via samples. Okay, so we can draw IID samples from this distribution. We have access to n of them. And we like to estimate some kind of symmetric property, which is a property that's invariant to permutation of the labels, right? There are many such properties. For example, the entropy, different versions of entropy, the support size, support coverage. It doesn't matter what the precise labels are. It's just a function of the shape of the distribution, and those are the kinds of properties that we're going to talk about. So we're going to be interested in this notion of profile maximum likelihood, and we'll say in a little bit how this plugs into what I said before, which is property estimation. But for now, I want to tell you what profile maximum likelihood is. Okay, so let's start with some simple example. Let's say you had a domain of 3 elements, okay, A, B, and C, and we receive, let's say, 3 IID symbols from this distribution, and they happen to be A, B, A. So that's our string of little n symbols, A, B, A. I'll say the profile of this set of samples is 2, 1. It's just recording the fact that we saw one element once and one element 2 times. Okay? Sometimes it's called the pattern, sometimes it's called the histogram. We'll call it the profile. Okay, so one notion that you might associate with a sequence of samples is what's the probability of seeing this particular sequence A, B, A. Okay, so well, let's say PA is the probability of seeing A, PB is the probability of seeing B. The probability of seeing this particular sequence ABA is just PA squared times PB. Right? Straightforward. All right. What's the profile probability? Well, now I say look at all possible sequences of samples where one element is seen once and one element is seen 2 times. Right? Look at all possible sequences of 3 samples that have the profile 2, 1. What's the sum of the sequence probabilities of all of these sequences? That's the probability of the profile 2, 1. Okay, so I distinguish between 2 things. One is what's the probability of this particular sequence, and what's the probability of this particular profile 2, 1. Okay, clear? All right. So just to clarify, what are the sequences that have the profile 1, 2 or 2, 1? Well, you've got to see 2 elements, 1 twice, 1 once. So you could have 2 A's and 1 B, 2 A's and 1 C, 2 B's and 1 A, 2 B's and 1 C, 2 C's, and so on and so forth. And each of these actually can be permuted in 3 different ways. So if you had AAB, it could be that the B appeared in the 3rd position, the 2nd position, the 1st position. Okay, so there are all of these different things, and you've got to add up all of their probabilities, right? Okay, good. So then the probability of the profile 1, 2 is going to be 3 times the sum of all of these terms. Right? Just to belabor the point, just to make sure that we're all on the same page. Okay? Questions? Okay, so now, given any sequence, look at its profile, and now let's ask these 2 questions. Right? Given a particular sequence, what's the underlying probability distribution that maximizes the probability of this particular sequence. Right? What do you think? I saw 2 A's and 1 B. What's the underlying distribution then? It's just the empirical distribution, right? So the sequence maximum likelihood, it's very easy. It's just the empirical distribution. If it was 2 A's and 1 B, then the empirical distribution is 2/3, 1/3. That's indeed the maximizing distribution. Okay. The profile maximum likelihood instead says, give me that distribution that maximizes the probability of the profile. In this case, the profile was 2,1 or 1,2. Okay. Clear? Somewhat different question from the first one. I'm going to ask the same thing now. What's the underlying distribution that maximizes the probability of the profile? What do you think? Sorry? Uniform. Okay, that's a good guess. So indeed, in the case of the sequence ABA, the empirical distribution maximizes the probability of the sequence. But somewhat surprisingly, if you haven't seen this before, the uniform distribution on 2 elements actually maximizes the profile probability. Okay? And there are other interesting things. Let's look at another example. What if we had A, B, C, A? So one element appeared twice, one element appeared once, and one element appeared once. And what do you think? Well, we know what the sequence maximum likelihood is, just the empirical distribution. It's going to be half, 1/4, 1/4, right? What do you think the profile maximum likelihood is? So this one is really surprising, even more surprising than the previous one. Okay, so notice that I haven't actually, well, I didn't say this, but I'm not actually constraining the size of the domain when you try to maximize the profile maximum likelihood. Okay, so even though I saw only 4, I had only 3 elements that I saw in my sample, I'm not saying that you have to have only 3 elements in your distribution. Okay. In fact, the profile maximum likelihood distribution in this case predicts that there are some unseen elements. There are some elements of the domain that you haven't seen in your sample. Okay, so it's actually predicting the distribution, the uniform distribution on 5 elements, which is a really surprising fact. It's sort of a nice feature of profile maximum likelihood because in reality, for many distributions, when you draw a sample, you're not going to see everything in the distribution. And so this has this interesting property that it's actually predicting this phenomenon of unseen elements. Okay? All right, so I just want to tell you that there is this notion called profile maximum likelihood. It has some interesting properties and somewhat unintuitive but interesting answers for these simple questions. Yeah?
Does it ever predict more than the support size squaring?
Probably not. Can't think of an example or proof off of my head, but I don't think so. Yeah. So people have studied these things. This was, well, maybe I'll say a little bit about it. I'm not going to say that much, but let me say one thing that's relevant for our talk, and we'll come back to this in a second. So if you look at this quantity, what's the profile maximum likelihood for a given probability distribution P? If I give you a distribution P on the domain, and I give you a profile phi, and I could say, what's the probability that when I draw from P, I see a sequence whose profile is phi, right? That, it turns out, is a combinatorial term that depends only on phi, and a second term, which is a permanent of a matrix. Okay, and what is this matrix? This matrix is a certain Van der Monde matrix that we'll come back to later in the talk. But there is the profile maximum likelihood, the objective function, is proportional to the permanent of a certain matrix, okay, which is a function of P as well as phi. All right? So for a fixed matrix P, right? For a fixed distribution P, we know how to approximate this permanent arbitrarily well. Jerem-Sinclair-Vigoda, for example, will do this. But notice that in our case, we don't have a fixed P. We actually have to figure out what's the maximizing P. Right? So even though we have a really good algorithm to estimate this arbitrarily well, we don't know how to do the maximization over all P necessarily via this route. Okay? So a bunch of heuristic algorithms have been proposed for this. So the original paper that proposed profile maximum likelihood as an interesting object of study was a paper by Alon Orlitsky and his collaborators back in 2004. And they suggested an expectation maximization heuristic to compute this. More recently, Vontobel suggested something called the Betti free energy approximation of the permanent as a route to getting good algorithms. And more recently, another paper due to Saki Weissman and his collaborators gave a dynamic programming algorithm. All of these are all heuristics. People experimented with them. As far as we know, we don't have any guarantees on any of these methods. Okay. All right. So, so I talked about two things. One is I talked about property estimation, and I talked about profile maximum likelihood, and I want to tie the two of them together. Okay. So, so remember, our goal was to really estimate some symmetric property of this distribution via access to samples, right? A variety of these problems have been studied for various properties of interest, and typically the results are of the form: here's a property of interest, here's an estimator, here's how many samples you need for that particular property. And people have really studied this to death. We know the exact, we are matching upper and lower bounds for many, many properties of interest: support coverage, entropy, distance from uniformity. But all of these are typically custom estimators that are designed for that particular property. Okay, what would be nice is to come up with some kind of method which can be applied to any property. Right? And so, in fact, there is such a proposal for a universal property estimator, and it goes via profile maximum likelihood. Okay, and this was established in a very nice paper from 2016, again by Alon Orlitsky and his collaborators. It's the same group of researchers that introduced profile maximum likelihood in the first place. And what they said is the following. Okay, so their result says, take any symmetric property of interest. If you knew that n was the optimum sample complexity for estimating this property within some accuracy epsilon, okay, then what you could do is the following. As a black box, forget about this particular property, just compute the profile maximum likelihood distribution and compute the property on this profile maximum likelihood distribution and report that as your estimate. Okay, so as a black box, compute PML, report the value of the property on the maximizing distribution. Okay? And this thing roughly will use up the same number of samples. Maybe you blow up the number of samples by a factor of 2 or something. And the error blows up, let's say, by a factor of 2. Okay, so you can get essentially the same kind of complexity as your optimal estimator by using this universal method. Right? Now, there's some technical caveats that I will shove under the carpet, but that's essentially the message of this result. Okay? And this makes computing the profile maximum likelihood distribution a very interesting question. So not only is it a sort of an interesting question in its own right, maybe it's kind of an interesting question, mathematical, combinatorial, whatever, but there's an interesting application here. If you could do this, then you could use it as a universal property estimator. And here's something that's even more surprising. Okay, so I said if you could actually compute profile maximum likelihood exactly, then you could use it in this way. It turns out that their proof is quite robust. It's actually a very simple proof. I encourage you to go read it. But the proof also says that you don't have to get it exactly. It's okay to even approximate profile maximum likelihood even to a huge approximation factor. So even if you approximate profile maximum likelihood to a factor of exponential in something better than n, okay, exponential in n turns out to be trivial. If you did just a little bit better, then you would have this result. Okay, so the only caveat is there is this accuracy parameter epsilon. Okay, and this epsilon depends on how well you're able to approximate. Okay, so if you don't have a very good approximation, then this will only work for very large epsilon. And if you are able to do a better and better approximation, this will work for smaller and smaller epsilon. Okay? All right. One thing I should point out is that via this particular technique, if you were able to get PML exactly, this is no different from getting a exponential in root n approximation. As far as this result is concerned, it's indistinguishable, right? It's almost the same thing.
So beta approximate means that the ratio of what you get to the maximum is beta?
Yes. Beta approximate means if you look at the objective function of profile, the objective function, that is at most within a factor of beta of the optimum value. Okay?
The first theorem only holds when epsilon is foregrounded,
This theorem holds only when epsilon satisfies this condition.
is it known when epsilon is smaller if the top theorem does not hold?
Yeah, not clear actually.
So actually this last statement also it's not clear if root n is
So what I meant is via this result, if you had to plug in an approximate version of PML, you'd get no better result from root n exponential and root n approximation. That's all I'm saying. But you're right that there could be some other proof that says that even for very tiny epsilon, this PML approach could work. Plausible. We don't know. Okay. All right. Okay. So two questions, right? So and I'll try to answer both these. One is, can we get rid of this condition on epsilon? And I'll give you some response to that. And the secondly, and maybe the most interesting question here is, can we actually compute such an approximate PML distribution? Because so far I just told you, well, there are all these heuristics and we don't have any guarantees on them, right? And this is the kind of guarantee that we want. We want to be able to say that what we output is within a factor of e to the n to the something better than 1 approximate version of PML. All right? Okay, is the setup clear? Questions? Yeah?
I'm a little confused about what it means for the property to be approximately, like what if it was like a Boolean thing?
Okay. So I was deliberately vague in saying that. So we're trying to estimate some property, right? So it's some number. And I believe the measure of accuracy here is an additive measure. So if we're within an additive epsilon. Okay? Yeah, it's not going to be terribly important for our talk, so I'm not going to elaborate too much. But so what we'd like to do is we're going to estimate this value, right? We want to estimate with a certain number of samples. Obviously, the more samples you have, the better estimate you'll get. Okay? Suppose we had an estimator which was guaranteeing a value within a factor of epsilon, then can we get this guarantee via PML? And that's what this result says. This result says that yes, you can get the guarantee with a slightly worse epsilon, with slightly more samples by using this black box method.
So here, I don't think, thinking of it as Boolean is maybe the best way, because you need some sort of tolerant measure that, allows you to change the distribution somewhat. So there, you can think about entropy, but he also had support size. And there, it's not saying, is the support at least, 100? That's, a question that you really can't answer until you get tons and tons of samples compared to whatever the smallest entry is. But it needs to be some kind of smooth measure a la property testing.
Yeah. So as Ankur pointed out correctly, there are actually some technical conditions here which I shoved under the carpet. which is this result only holds if you have some certain smoothness of your property and so on, right? But that's not going to be terribly important for us, so yeah. Okay. All right. So I want to give you two responses. One is I'll say a little bit about how we might get rid of this condition on epsilon by changing the notion of PML a little bit, and I'll do a very quick first segment of my talk on this. And for the most part, I want to talk about computing an approximate PML distribution. Okay, and I'll talk about two different results on this. One is a result that appeared in Stock earlier this year, where we gave the first provably approximate algorithm for profile maximum likelihood, and the factor that we got was exponential in n to the 2/3, roughly speaking. And I'll talk about a new result where we were able to improve this to exponential in root n. And the interest is not so much in the fact that we improved this, but I think the proof technique and the connections that emerge are actually more interesting than the result itself. This first talk I actually gave here in this room about 1.5 years ago. So I realize not many people in the audience were there. So I'll skim through this up without getting into it in much detail. Most of my time I'll spend on this newer result. Okay? All right. So before I delve into those details, I should say, there are a few different ways in which people have tried to approach this. Can we get a universal estimator for symmetric properties? Profile maximum likelihood is one approach that was advanced by a bunch of people, but the big question there was, can we actually get an efficient algorithm? Okay, so we didn't have an efficient algorithm, which is something that we addressed now. Another approach that's been proposed is a linear programming approach, and this was originally proposed by Efron and Thiested, and this was also featured in work by Paul and Greg Valiant from 2011. And roughly, they tried to write a linear program to find a distribution that's consistent with the observed frequencies. And if you actually work out what the dependence is on epsilon, they get a somewhat suboptimal dependence on epsilon. There are these custom estimators that have a much better dependence on epsilon. And there's another approach, which again I won't say much about, but I just want to mention that there's another line of work in this area based on what's called the approximation approach. They try to prove some kind of minimax upper and lower bounds for various functional estimation problems, use things like local moment matching, concentration inequalities, and so on and so forth. And this also applies to the Gaussian setting. And what I'm going to describe, profile maximum likelihood and so on, is very much applies to a discrete setting. Okay, so profile maximum likelihood is one of several approaches that have been used in this area. I think it's an interesting approach, and so we're going to focus on this one. Okay, but there are others. Okay, so let me say a little bit about ways in which we might actually get rid of epsilon. I said that there is this barrier. We can't get epsilons to be very small. So here's one approach that we suggested in some recent work of ours. Okay, so here's how you might get a property-specific estimator for a particular property f. So you have some property f of interest, right? One natural thing to do is to just use the empirical distribution. Right? Actually, if you take enough samples, the empirical distribution is going to be a pretty good estimate of the actual distribution, and then that'll give you a good estimate of f. The trouble is this needs way too many samples, right? And for many properties of interest, you can make do with much fewer samples than you need to get the empirical estimate to match up. But there are various things that you could do. You could sort of take the empirical estimate and do various sophisticated massaging on your empirical estimates to do better. Okay, so that's one. And in fact, many of these property-specific estimators do exactly this. They take the empirical estimate, and somehow they apply some sophisticated tools to massage these empirical estimates. Okay, so what we're proposing. What we proposed is a sort of a very simple approach, which was for some range of frequencies, take the empirical estimate, and for the other frequencies, take the profile maximum likelihood estimate. Okay, so for example, you could have some properties where you cut off at about, let's say, 10 log n. Okay, every frequency that appears elements that appear more than 10 log n times, the empirical estimate is pretty good. You can use that as your estimate of the probability. For all the frequencies that are less than 10 log n, we're going to do a PML on that. Okay. Now, where exactly you cut off, which ones you apply the empirical estimate to, and which ones you apply the PML to, is a property dependent thing. Okay, so there's a slight property dependence here, which is based on the property you decide which frequencies you believe the empirical estimate for, and which ones you need to apply PML for. Okay, for some weak dependence on the property, but for many, many properties of interest, this thing can really result in a huge improvement in the running time, for example. Right? You typically have to apply profile maximum likelihood for a much smaller set of frequencies. You don't need to apply it to the entire set of frequencies that you observe in your sample. Okay? And a very similar approach has been suggested by independent work, and they call this truncated PML. Okay, so just to give you a sense, this is something that's very practical. You can run this on various things, and we did. What ends up happening is what you expect. For a large fraction of your frequencies, you can actually apply the empirical estimate and use that. You only have to apply PML for a very small fraction. So these are the fractions on which we had to apply the empirical estimate. When your sample sizes get very large, we actually had to apply PML on a very small fraction of the data. Okay? And our experiments show that actually this method works extremely well. Okay?
MFRAC is the fraction on which you don't apply a PML?
MFRAC, yes. MFRAC is the fraction on which we apply the empirical estimate. So 1 minus that is the fraction on which we apply. Okay? So this is one way in which you can get around this the issue that I mentioned earlier, which is that if you use that theorem as a black box, then it only applies for epsilon that's large enough. Using pseudo PML can get around this problem, because actually now we're applying pseudo PML on actually a very small set of frequencies. Okay? All right, so that's one idea to keep in mind.
Can I see it a second?
Sorry.
So are you always you're always overlapping with the valiant and valiant?
No, actually, good observation. We're always overlapping actually with this one, which is PJW17. Okay? So let me explain what's going on in this plot. So I said, here's what we're going to do. Let's say we're trying to estimate entropy. These are all for entropy. So we're estimating entropy. We're going to have a cutoff. For the very high frequencies, we're going to say we're going to use the empirical estimate. For the low frequencies, we're going to use PML. Okay? Okay, now which PML estimator do you use? I didn't tell you that. Right? What estimator do you use? So for these experiments, what we did was we plugged in a heuristic estimator that existed in the literature. Okay? And the one that we used was actually this paper, PJW17, which is Pavlikin, Jiao, and Weisman. Okay, this is a very fast dynamic programming approach. Okay, so it doesn't have a guarantee. All right? Theoretically, there's no guarantee. Empirically, our performance matches applying their dynamic program on the full distribution. So in fact, we track their performance very, very closely. So all we're saying is that you can take this heuristic, chop off the very high frequencies, just use the empirical for that, apply the dynamic program actually on a very small portion, and you'll actually get essentially the same performance. But you get a much bigger, you get a speed up. Does that make sense?
Speed up
I'm
is relative
confused.
to the
I'm super confused.
Relative to theirs, yes.
Your algorithmic contribution is the threshold?
No. The algorithmic contribution, yes, is saying that you can chop off the frequencies and just apply it to a small set. Now, you can plug in whatever you want over there, right? For our experiments, we chose to apply this dynamic program. But you could apply the algorithms I'm going to describe next.
So here I think there's two separate things, because there's the stuff with guarantees and then the heuristics for the experiment. I mean, the thing which is at least partially heuristic for the experiment. So I guess the main thing is the range of epsilons for which you can compete with the optimal thing, which then when epsilon is tiny, then you're getting some giant polynomial number of samples. So empirical is quite good, so it's not a priori obvious if like the profile maximum likelihood or anything like that is the right thing to do when you have like tons and tons of samples.
So you could plug in a heuristic for what you do for PML, as we did here for the experiments. You could also plug in a method that has theoretical guarantees, like the ones we're going to describe next. Okay, but we didn't do that in the experiments that we reported, right? And if you did plug in a method which has guarantees, then you could ask the question, now for what value of epsilon is this valid? And you can get this to work for much smaller epsilon than you did before. Okay? All right.
Maybe this question is completely misguided, but I'm just going to ask it.
Yeah.
So what happens if you plug in like random noise for the high frequencies?
What do you mean by random noise for the high frequencies? I don't understand.
So you're saying that for the low frequencies you're using this PML, and then for the high frequencies you're using the empirical.
Yes.
But I mean, like there should be some kind of a null case in which you plug in garbage for the high frequencies and see what happens.
I'm not sure I understand the question. Because the whole point of, in this case, for entropy, right, the whole point of cutting off at some point and saying these are high enough that I have good confidence in their probability values. The empirical estimate is actually going to be pretty good. So from the empirical estimate, I have a very good idea of what this contributes to the entropy. And so I don't understand what you mean by plug-in noise. Well, we can take it offline.
P is the largest probability, for example, and you have a Dirac that is 0, like you only see 0. Then if you, for this one, you would be tempted to plug in a random number rather than just the proportion of zeros that you see.
I mean, just for these specific experiments, like what would happen if you just plug them in?
Depends on the functional. If your functional only cares about the small values, then I guess.
Then it's fine, yeah.
No, I know, but I was asking
Oh, for
specifically
here.
for these plots.
Oh, for these guys.
Yeah.
I'm not sure.
Because I want to compare to something that's like clearly.
I mean, the high frequencies by themselves have a lot of contribution. Now, if you plug in random noise, maybe the noise cancels off. I don't know. Okay, but we can discuss offline. All right. So I still have
Until
15. Okay, good. Let me talk about ways in which you can actually approximate the PML objective. Okay, so remember, prior to our work, the open question was, can we even get anything slightly better than e to the n? Okay. All right. So I want to give you an outline of how our previous result worked, and this was stuff I talked about here in this very room about a year and a half ago. Okay. So we showed that you can actually get an approximation to within a factor of e to the n to the 2/3. And here's sort of in a nutshell how this method works. Okay. So if you look at this PML objective, right, there is some matching between the frequencies. Think of these are elements that you saw once, twice, 3 times, 4 times, and so on. These are the elements you saw nj times in your sample, and these are your underlying probabilities in your distribution. These have probabilities pi, these have probabilities pi plus 1, and so on and so forth. Okay. So you have these frequencies on the top, you have these probabilities at the bottom. Okay. The first step that we did, and this was really crucial in our method, was a very simple thing, which is we just discretized these frequencies and these probabilities. Instead of these frequencies taking every value between 1 and n, we just said let's discretize them so that they come from some geometric series. Okay. Same for the probabilities. All right. So we lose something in the process, but we can control how much we lose. And now let's look at the setup where we have discretized probability values, discretized frequency values. If you want to compute this PML objective, what you have to figure out is, of all the elements that you saw nj times, how many of them came from this set of probabilities? How many of them came from this set of probabilities? How many of them came from this set of probabilities? Right? You need to populate this bipartite graph between the the top and the bottom. Okay, right? For every way of populating this bipartite graph, there are many, many choices of elements at the bottom that can appear on the top. So there's a certain contribution to the PML objective that comes about from any way of populating this bipartite graph. Okay, so there's a bipartite graph. It's got some constraints on this side and this side. You know exactly how many elements need to appear here, which means the sum of all these edges is constrained. You also have some constraints on the bottom, which means that the sum of the probability values has to be close to 1. Okay, so there are constraints on both sides. For any way of populating this bipartite graph, you get a contribution to the PML objective. And what we want to do is we want to sum up over all possible ways of populating this bipartite graph of the PML objective, right? Okay, so first thing we did was we said, okay, this seems like a complicated problem. How about let's just look at the largest possible term. Let's look at one term in this PML objective. Okay, and we argued that there aren't that many possible bipartite graphs here. So by just focusing on one term instead of the sum of all these terms, we don't lose too much. Okay, and then for this one term, we looked at this objective. We wrote it down, and we came up with a convex relaxation for this objective. Okay, we solved this convex relaxation. We got some continuous values. We rounded these continuous values. We lost something in all of these steps, but overall, we were able to manage the total loss and argue that the total loss is no worse than e to the n to the 2/3. Okay, that in a nutshell is how our algorithm proceeded. Okay, so initially, you know, our objective function was the sum of probabilities of everything. We grouped these terms into groups exactly by this bipartite graph that I mentioned. Then we looked at the maximizing group, one term. For this maximizing group, we wrote down a convex relaxation, solved it, and we rounded it. Okay? That's how our algorithm worked. Okay, so I'm skipping over lots of details. All right, now let me tell you how the new result works. Right? So really the old result was all about looking at this objective, using, you know, things that are in the computer science, theoretical computer science toolkit, discretization, simple counting things. Okay, so now I want to show you a slight improvement to the result, which I think has interesting structural properties. Okay, so I want to prove that we can actually get exponential in root n approximate PML. Okay, so here's what we're going to do. Given this profile phi, for a fixed p, I said that the objective function for PML is actually proportional to the permanent of a certain matrix. Let me tell you what this permanent is. All right? So it's the permanent of the following matrix. This is a D by D matrix, where D is the domain. Okay? And the xyth entry of this permanent, so is the probability of x raised to the frequency of y. Okay, so p of x is the probability attached to element x in the distribution. F of y is the frequency with which you saw y in your distribution. Right, so the columns correspond to the frequencies, the rows correspond to the probabilities, and the xyth entry is the probability px raised to fy. Okay? Then the PML objective is really proportional to the permanent of this matrix. Okay, it's not very hard. Yeah.
Remind us what the frequency means here?
Frequency means the number of times you saw element y in your sample.
Okay, so how does phi show up here?
Phi is the vector of frequencies.
I see, okay.
Right? Phi is the profile. It's just the vector of frequencies.
Oh, I see, okay.
I mean, it's sort of this, it's a thing where I forgot which element appeared which times, right? That's what phi is.
But is it really indexed by D? I'm confused now.
Sorry, is what indexed?
So I thought thought the profile was just telling.
Okay, you're right. In some sense, when I said the profile, I said we ignore, we forgot information about which element appeared how many times, and I just remembered how many elements did we see once, how many elements we saw 2 times. Okay, this is a little bit of a lie, this notation, right? But just bear with me for the talk, right? What we're going to do is we're going to define this matrix, where the matrix is the following, right? I have my sample. In my sample, I know which element appeared how many times, right? Let Fy be the number of times element y appeared, okay? I also know my underlying distribution. Let's say I know my underlying distribution. Px is the probability attached to element x in the domain. And just define this matrix, where the xyth entry is Px to the power of Fy. And now I'm saying the quantity of interest is the permanent of this matrix, okay? All right. So what we're going to do is we're interested in the permanent. Permanent is kind of this complicated quantity that we don't quite have a handle on. Instead of looking at the permanent directly, we're going to use some approximations to the permanent, right? And we're going to use 2 well-known approximations. One is called the Betti approximation, and the other one is called the Sinkhorn. That's a spelling mistake approximation. Okay. Now we also want to do the following, right? We want to compute the probability P that maximizes the PML objective, which means we want to compute the probability P that maximizes the permanent of this matrix. Right? So this matrix is parameterized by P. I want to find what values of the probabilities should I pick so as to get the largest possible permanent value. Okay. So in order to do that, we're going to use the same ideas that we had before, which is we're going to do some probability discretization and do some sophisticated rounding algorithm. Okay. This part is something that we're not going to focus on that much today. Okay. But that's what we'll have to do to actually maximize over all the distributions. Okay. So what I want to do now is I want to relate the permanent to these Betti and Sinkhorn approximations. So my objective function, ignoring some combinatorial term, is really the permanent, right? There are these approximations to the permanent. What I'd like to know is how good are these approximations relative to the value of the permanent? What's the gap between them? Okay? All right, so let me tell you what these approximations are. Okay? So some of you might have seen them before. So for any matrix A, the permanent is just take all possible permutations and sum up the generalized diagonal, the product of the entries on the generalized diagonal corresponding to that permutation, right? Sum over all permutations. So that's the permanent. Okay. Okay. So I'm going to define 2 quantities. One, take a doubly stochastic matrix Q. So Q is a D by D matrix. Okay. It's doubly stochastic, rows and sums, column sum up to 1. And look at the following quantity: summation qxy log of axy divided by qxy. Okay. Let's call this uaq. All right. And another quantity v of q is just the sum over all of the entries xy, 1 minus qxy times log of 1 minus qxy. Okay, so these are 2 expressions. Now, the Betti approximation is just the maximum over all doubly stochastic matrices Q of exponential in uaq plus vq. Okay, so that's what the Betti approximation is. The Sinkhorn approximation is max over q, doubly stochastic q, of exponential in just the first term. Okay, so it doesn't have the second term, just the first term. All right. Now, there's another way to think about the Sinkhorn approximation, which is maybe one that you might be familiar with, which is you can try to normalize, scale the rows and columns. Right? So think about scaling the rows and columns of a matrix. So if you just take a particular row and multiply all of its entries by alpha, what does that do to the permanent? Well, it scales it by alpha. If you take a column and multiply all of the entries by beta, what does that do to the permanent? Well, it multiplies it by beta, right? So it turns out there's a way to scale the rows and columns simultaneously such that you get a doubly stochastic matrix, right? When you get a doubly stochastic matrix, you have a very good handle on what the permanent is. It's not trivial, but it's known that if you have a doubly stochastic matrix, the value of the permanent is between 1 and e to the minus n. Okay? So given that you know what the permanent of a doubly stochastic matrix is, it's sandwiched between 1 and e to the minus n, you know the permanent of your original matrix is approximately the product of your row multipliers and your column multipliers. Right? So this is called Sinkhorn scaling. In fact, you can think about Sinkhorn scaling as optimizing this particular function. Okay, so it turns out that what I just described is actually equivalent to this procedure. Okay, so even though it's expressed maybe in a language that you may not have seen before, this is really the same thing. It's expressing what this Sinkhorn scaling is doing. Okay, I'm going to, for our purposes, we're going to be interested in a slightly different version of, this is the usual Sinkhorn approximation, but I'm going to look at a scaled Sinkhorn approximation. So remember I said, in the Sinkhorn iteration, when you get down to doubly stochastic matrix, the value of the permanent is between 1 and e to the minus n. Okay? The Sinkhorn value will give you 1 for a doubly stochastic matrix, right? It won't do anything. It'll just give you 1. Okay? What we do is we subtract out n, which means in the Sinkhorn, in the doubly stochastic case, instead of outputting 1,
maximizing your lower bound.
exactly, right. So we're going to move our lower bound to e to the minus n. Okay? So Sinkhorn by itself is not a lower bound on the matrix, on the permanent, but the scaled Sinkhorn is. Okay? All right, so we're going to look at the scaled Sinkhorn version. Okay? All right, so this is a very non-trivial fact which was originally proved by Gurwitz in 2011 using a certain powerful inequality established by Scriver. He showed that the Betti approximation for the matrix is always a lower bound on the permanent. Okay, and now we know several alternate proofs of this, and some of these alternate proofs use various properties of real stable polynomials and so on. So it's a very interesting inequality in itself. It was first proved by using some pretty heavy-duty methods, and now we know some other alternate ways to get the same fact. Okay, so it turns out that the Betti approximation is indeed a lower bound on the permanent. Okay. There's also some simple relationships between Betti and Sinkhorn. So if we look at the scaled Sinkhorn version, the one where we translate Sinkhorn by some quantity, the scaled Sinkhorn is always less than equal to the Betti approximation, which means that the scaled Sinkhorn approximation is always less than equal to the permanent. All right. Here's the best known upper bound that we know on the Betti approximation. So first of all, an exponential bound 2 to the n, e to the n is very easy, relatively easy. The best known, and in fact tight bound, is due to Anari and Rizai. It's going to appear actually in Fox in a couple of weeks, I think. They showed that the Betti approximation gives you a root 2 to the n approximation. Okay, so in fact, here's what we know about the permanent. It's sandwiched between the Betti approximation and root 2 to the n times the Betti approximation. Okay? For our purposes, this doesn't really do anything for us, because remember, we want something which is exponential in something a little better than n. All right, so this is not quite what we want, but hold on a second. Okay? Any questions so far? Okay, so here's what we can show. This is our result. Turns out that the scaled Sinkhorn approximation with the matrix A, we already know this one I showed you on the previous slide, right? as an upper bound, we can say that if A happened to have at most k distinct columns, then the approximation factor is exponential in k log n over k. So think of it as a n over k to the power of k approximation. All right? So provided your matrix A had a small number of distinct columns. Okay? Now think back to what the matrix A was. Matrix A was this matrix which had probabilities on the rows, frequencies on the columns. Okay? I give you a set of n samples. So I have frequencies corresponding to n samples. How many distinct frequencies can I have? That's the number of distinct columns that I have.
Root m.
Square root n. Yes. Okay. So in fact, that's what we're going to use, and that's why we're going to use this theorem. Okay. So before I tell you that, from this result on the scaled Sinkhorn approximation, we have the same result for the Betti approximation, right? The Betti approximation we know is a lower bound in the permanent. Scaled Sinkhorn is less than equal to Betti. That gives us this inequality, and so we have the same result for the Betti.
By the way, so what's known about the computational aspects of the Betti approximation? So for Sinkhorn, then you get it just from matrix scaling. Can you compute that the thing in the maximizer?
I think you can do that for Betti as well. I'm not 100% sure. I think you can. Yes. Okay. These results in this form are also typed. Okay, so it turns out there is actually a matrix A which has k distinct columns, for which you can show that this upper bound is typed. Okay, so in general we can't hope to do better than this k log n over k. All right.
This is the only structure of the matrix that you have to compute that you use?
This is the only structure of the matrix we use. Yeah. Yeah, it's
in particular, if you knew, like, so as statisticians, we like to think, what if nature was nicer to us, which is not how you guys think. But like, for example, if you had like a p that would take just a small number of values, like if you had like a piecewise constant distribution,
that's great.
then you would take advantage of that
Yep.
as well, right? Because
Yep.
row and columns are indistinguishable.
Yes, exactly. Yes, if you had a small number of probabilities, that's great. That's also very useful. That I mean the bound would immediately imply that you get something better. Okay. And by the way, this also means, going back to pseudo PML, right? When I described it earlier, remember we said we're going to cut off at some point, right? And we're going to only apply PML for a small set of frequencies, not for the high frequencies. This means the number of distinct frequencies is even smaller. It's only log n, right, or 10 log n. And so again, this is helpful for this bound. Right? Yeah. Okay. All right. I should try to try to be a little bit faster. Okay. So as you concluded earlier, in fact, this form of the bound is particularly nice for us because for any set of samples where we have n samples, we know that the number of distinct frequencies is at most root n. So that immediately gives us this e to the root n from this result. Okay. I should say that this Betti and Sinkhorn algorithms were proposed as heuristics for profile maximum likelihood by Vontobel. In fact, he designed these methods to approximate these to compute this. But his methods are actually heuristic methods. They're sort of these alternating minimization methods, okay, where you fix the p's and optimize. Well, you fix one quantity, optimize the other, fix that quantity, optimize the first, and so on. As I said, we need to. All the stuff works for a fixed p, and this is good for our proofs here. But we need to maximize over all distributions p, and that requires some other ideas, which I'm not going to get into. Okay. All right. Here's the matrix that optimizes this bound. Let's not worry about it. I was going to give you some idea of the upper bound, but I don't think I'll be able to do it in 2 minutes. So I'm just going to flash it, and you can read the details in the paper, which hopefully will be on the archive very soon. The key idea is to somehow take this matrix A, which has a small number of distinct columns, and define a certain doubly stochastic matrix. Actually, not quite a doubly stochastic matrix, a matrix that has row sums 1 and column sums phi j, where phi j is the number of times the element j appears. We need to somehow use this particular, we need to define a suitable matrix P that has these row sums and column sums. And that's the one that guarantees that, so remember the scaled Sinkhorn is a maximization problem over all doubly stochastic matrices of this quantity, right? What we're going to do is we're going to exhibit a particular doubly stochastic matrix that we can plug in here, okay? And that's what gives us the bound. So our goal is to find a special doubly stochastic matrix that we can plug in here, and that guarantees that the permanent of A satisfies this inequality, okay? Now, actually the construction is interesting in itself, but I think I'm going to skip it in the interest of time. I'm happy to tell you guys more if you want offline. So I'm just going to flash this. Sorry about that. Okay, I'll end with one interesting question. So we spent a lot of time thinking about how well can we approximate profile maximum likelihood. One embarrassing open problem, okay? Can we actually compute the optimum profile maximum likelihood objective in polynomial time? Actually, I don't know the answer to that question.
So at least in this form, it seems kind of optimistic, right? I mean, would you hope for a p-TOS instead, or you really?
I think the problem is hard. I don't know how to prove that it's hard. My guess is, okay, it should be hard, but we haven't ruled out a p-TOS. We haven't, for that matter, we don't have NP hardness, or the equivalent of NP hardness. Okay.
So here the difference is like rather than finding a solution, you want to just find the value? Is that what you're stating, or?
Yeah, let's say you just want to find the value. Okay. All right. So in case you want to follow up on any of these things that I mentioned, the first paper where we got this exponential and end of the 2/3 approximation appeared in Stock earlier this year. This paper on pseudo PML will appear in Europe's 2019. And the last paper that I spent bulk of the latter half of the talk on is still in manuscript form, and we hope to have it on the archive sometime soon. Okay. All right. Thank you.